Okay, so we are shifting gears from privacy to data augmentation, presented by Bruno and Max. So, sorry, Brandon and Max. Brandon is a PhD student in the machine learning department at CMU, advised by Professor Raslan Salahuddinov. And Brandon is a recipient of the NDSEG fellowship, and his research centers around using foundation models like Stable Diffusion to augment few-shot learning tasks. And Max is a student at University of Chicago Laboratory Schools. He's a collaborator with CMU and MPG range. So please welcome Brandon and Max.
Thank you for the introduction. So as she said, I'm a PhD student at CMU in the machine learning department, and I work with Russ, who's also here today if you'd like to chat with us. Our poster is in the back, and we'd love to come chat with you about collaborations or potential ways of using our augmentation if you have your own domain-specific data sets. Those are all things that we're really excited about. And today I'll be presenting our recent work on using Stable Diffusion to build an automatic data augmentation that adapts itself to the images in your data set and automatically infers the ways that the images in your data sets vary, the natural invariances present in the data set. So this paper was a collaboration with Kyle Doherty, who's a postdoctoral researcher at MPG Ranch, and who helped us collect a really interesting data set that my collaborator Max will help introduce at the end of the talk today. This is a data set where we actually applied our method in Montana to detect an invasive plant called leafy spurge. And also, Russ was a really great help on this project as well with advising. So let's talk a bit about data augmentation. What are the ways that people currently use to do data augmentation? Data augmentation is really interesting because it's one of the most widespread techniques in computer vision right now, and it's a very effective tool at increasing the performance of computer vision models in many different tasks and domains. It's very popular for classification, but also very widely used in other tasks like object detection, semantic segmentation, and it's almost a universal thing at this point to use data augmentation when training a computer vision model. Some examples of augmentations that are really popular in practice are using horizontal flips, rotations, recolorizations, and also there are several techniques that like to mix together the content of multiple images. So I've selected two very recent data augmentations from Kubuk et al. And Yoon et al. So that's RandAugment and CutMix as two examples. So we use these as baselines in our paper. And on this slide, we have some example augmentations that would be produced if you were to use RandAugment and CutMix on this image of a train. You'll get this rotation with a sepia effect. This can be sampled by RandAugment, which composes together multiple simpler transformations. And for CutMix, you'll get things that tend to paste together different crops of images. So these augmentations are very performant and very easy to use, but there can be some issues with them sometimes. Depending on the augmentation that's sampled when you use CutMix and RandAugment, sometimes they can remove information that might be important towards your computer vision task. If you have a data set, for example, let's say you're classifying species of flowers, sometimes the color of a flower and the shape of a flower together will be important for determining its species. This can be information that RandAugment can remove if it samples a transformation that changes the color of an image. And that can be harmful in this specific case and might mean that this augmentation in its base form is not suitable for this kind of data set. In addition, CutMix as well and augmentations that paste together images, these can also potentially destroy information in an image. If you have a data set that has very localized class information, let's say that an object is very small in your image, CutMix might paste something onto that object and could completely eliminate it from the image. And in that case, you might end up with an image that only has information from the paste and doesn't have the original class. And CutMix might not be suitable for this kind of data set either. So these are two examples of how these current augmentations sometimes require a good intuition about your data to know when they're suitable to the problem. What we want to do to approach this problem is to try to remove the intuition that you need about your data and try to build augmentations that instead automatically adapt themselves to your data sets. And we want to do this in as minimal of a way as possible that doesn't require much information about the data set or much expert knowledge. So what that corresponds to in this example with an image of a train, let's say we start with this image of a train on the left. We want an augmentation that learns from this image, identifies that this has a train in it, and figures out on its own the key invariances that trains have and modifies the image accordingly. So what that looks like with our augmentation, we'll talk about how this works in the next few slides, is that our model identifies that trains vary by having different coats of paint, different layouts for doors and windows, and changes in the background as well, like the layout of the tracks, the clouds, and also the trees in the background. And importantly, our method does this without any prompt engineering, and it's fully automatic and data-driven. So we're going to start in our pipeline with a set of real images that are taken from a few-shot classification data set. Few-shot is very important in our setting because often in practice it's very costly to collect a lot of images. So we want to make the assumption that we have as few images as possible. So these are going to be a few training images from our data set. And in this example, these images are for classification of different forest biomes. And what we want to get to is a set of augmentations from these source images that have key differences like the time of day. For example, on this image on the left, you'll have the same forest but at night, and also potentially different weather conditions like snow. And we're going to present an augmentation based on a pre-trained Stable Diffusion 1.4 checkpoint from Hugging Face that we use as a data augmentation engine. And we'll talk about the different design choices and trade-offs associated with designing such a data augmentation. The key idea with our approach, DA Fusion, data augmentation with diffusion models, is to use shared context in the images in your data set for controlling how those images are augmented. So our model has two parts. There's an adaptation component that takes the model and adapts it to the content in your data set so that the model pays attention to, for example, if there's a train in your image, or in this image in particular, it identifies that this is an image of a cat wearing a bow tie. We'll talk about next how we generate those images, but let's first pay attention to the fine-tuning component. The way that this works builds off of an algorithm called textual inversion. It's also quite similar to an algorithm called Dream Booth, if you're familiar with that. We wanted to make our fine-tuning step as simple as possible and leave the weights of Stable Diffusion untouched so that our method is compatible with potentially other patches that people have made to Stable Diffusion. Those can just be plugged in. So what we do is we provide a prompt with a new pseudo token that we're denoting as Y on this slide that corresponds to each concept in your data set. So if you have a data set of 10 classes, there would be 10 pseudo tokens or pseudo prompts. We then optimize this pseudo prompt to minimize the standard diffusion loss and learn a representation for Y that corresponds to your image content. So if you show our method only this one image of a cat wearing a bow tie, after several iterations of gradient descent on this loss function, you'll end up with a representation for Y that resembles a cat wearing a red bow tie. But perhaps this is a bit too specific of a representation. What's really interesting about this procedure is that the more images that you observe, this representation changes and can become more accurate with respect to your data set. Let's suppose that we observe this image next of a person wearing a red bow tie. After you've provided this image, there's new context, and the model instead learns that who's wearing the bow tie is perhaps less important and updates the representation accordingly. And similarly, we can keep observing more images and this representation gets more and more refined. And let's say we observe all 4 of these. The model learns that what we care about is mainly the bow tie, not the color and not who's wearing it. So we talked about how we fine-tune our model to be good at generating augmentations. Let's now talk about how we take this fine-tuned token and apply it to generate augmentations in practice. What this looks like is starting from a source image in the training set of your few-shot task. And we're going to use this image as a structural guide for generating augmentations. We take this image and add a small amount of Gaussian noise, and then attempt to denoise this image with Stable Diffusion for several denoising iterations using the same pseudo prompts that we fine-tuned in the previous part. And we're going to do this for several steps until at the end we get a cleanly denoised image that is an augmentation of the original source image. Now there's an interesting controllability aspect here with this sort of augmentation approach that depending on where you insert the source image in the denoising process for Stable Diffusion. In other words, depending on how much initial noise you add to that image, it controls the extent of the augmentation and how strongly the image is modified. If you choose a very low insertion time step, corresponding to an insertion position far on the left, you'll get an image that looks almost the same as the source image, but very low level details are changed, such as the striping pattern on the fur of this cat. And as you increase this insertion time step, more and more information about the image is going to change, such as on the far right here, you can see that the bow tie is now much larger, and the cat is also having a vastly different coat of fur and a different pose as well. So this is how DA Fusion works. We have these two components. We have our fine-tuning component, and we have our generation component that we use to produce several different augmented versions of every visible image in the training set of your few-shot classification task. We take these two sources of images, your real images in your data set, and your augmented images, and we're going to combine these together in the next few slides and train few-shot classification models on a mix of real and synthetic data. We have this hyperparameter that we're using to control the mix of real and synthetic data. This hyperparameter is called alpha. And what we found in practice is that setting this to be 50% real, 50% synthetic data seems to work really well across a variety of tasks, as we'll see in the next few slides. So before we get to results, I wanted to present a few really cool demos of what DA Fusion can do. So if we start from the image on the top left and say this is our source image, let's say we use a very low insertion time step and we don't perform much augmentation, only a little bit, because we're using a low insertion time step. We'll get augmentations that look like these other 5 images. You can see that the placement of the trees in these images are in the same locations, but lower level details like the ferns on the ground and also the structure of the branches is different. So we've looked at how we can build an augmentation that adapts to your data set, and we're now going to talk about how augmentations from DA Fusion can improve few-shot classification performance. And we're going to look at 7 different tasks. We have 6 few-shot tasks adapted from literature that we chose to encompass a variety of concepts, some of which are very common, like cats and dogs. These are things that Stable Diffusion has very likely seen many thousands of examples of during training. And we're also going to look at data sets that have more fine-grained concepts that it's less likely that Stable Diffusion has been trained on. And finally, what my collaborator Max is going to talk about is a new data set that we worked with a team of ecologists at MPG Ranch in Montana to collect ourselves that represents a novel concept that Stable Diffusion has certainly not seen in its training, because we collected it this year and the data set is not currently public. So our evaluation protocol looks like this. We collect a handful of real images, or we source them from a standard data set, and we're going to use Stable Diffusion with our augmentation approach to transform these images semantically. And then we're going to train few-shot classification models on this mix of real and synthetic data. So evaluated across these 7 different tasks that I introduced, we see a very consistent improvement with DA Fusion. In this example, we're comparing with a standard data augmentation rand augment, and we consistently beat the rand augment baseline here. We also compared with a similarly capable diffusion-based augmentation called Real Guidance from a paper at iClear 2023. The main difference between Real Guidance and our approach is that their approach leverages prompt engineering instead of adapting the diffusion model to your data set. And what we find is that prompt engineering generally performs worse than our adaptation. And interestingly, for common visual concepts, we find that the prompt engineering solution generally performs very well. But as the concepts become more and more fine-grained, and it's less likely that Stable Diffusion has been trained at scale on them, as well as when these concepts become harder to describe in language, such as flower species, prompt engineering tends to fail. And our approach seems to perform well across all domains and has strong performance. So DA Fusion has really good performance across all these tasks, but another important aspect of a data augmentation to make it viable in practice is to be able to control how the augmentation works. And this is very important because real images are often cluttered and there can be distracting concepts. And you might want a data augmentation that transforms images semantically to be able to focus on only one of these concepts and ignore the other. For example, if we show DA Fusion this picture that has a dog and a cat, it's unclear, without providing any additional context, if this is the only image, which of these concepts the model should focus on when generating augmentations. The implicit solution here would be to select a better data set that doesn't have distracting concepts, but this is not a good solution because often collecting a data set is costly. And as Max is going to talk about, when collecting a data set in the real world, it can take a lot of human labor, and it's often not realistic to do this in every domain. So what else can we do? So in our paper, we look at an additional way to control our augmentation. When you have images that have some amount of ambiguity, our idea is that you can prompt the augmentation with additional context to help identify which objects the augmentation should focus on. So in the case of this image of a dog and a cat, we don't know which concept we should focus on purely from an augmentation perspective, but let's suppose we want to focus on the cat. If we use Diffusion out of the box, we haven't provided any additional context. It generates augmentations that have both cats and dogs. But if we want to focus the augmentation on just the cat, we can provide Diffusion with this additional context during the adaptation step of our method that tells Diffusion that the concept that we're trying to generate, i.e. our pseudo prompt y, it's to the right of a dog in the image. And if we provide Diffusion with this prompt, it's able to correctly identify to generate cats and generate augmentations that have the specific cat. So this concludes the main results section of our talk. My collaborator Max is going to go into more details on our real-world evaluation and what that looks like. But as a bit of a conclusion from my section, we're very interested in looking at other ways of using this augmentation. We have results on few-shot classification tasks, but we're very excited to look at how this can also be extended to tasks that have many more objects that might be distracting, or object detection and segmentation tasks. And if you're interested in any of those things, we'd love to talk to you back at our poster. And with that, take it away, Max.
Okay, thank you, Brandon. So, as Brandon just mentioned, one of our major motivations for this paper is this leafy spurge dataset, so I'm going to talk about that now. So leafy spurge is an invasive plant primarily in the Bitterroot Valley region of Montana, so that's in western Montana near the Montana-Idaho border. And one of the things about this plant, as you can see in both images here, is that it has this kind of distinctive yellow-green color when it's blooming. And this means that it's very easy for humans to recognize, even from drone images, as you can see in the right here. So to collect this data set, we surveyed 40 sites in a conservation ranch in western Montana. The image on the right shows exactly where those sites are within the ranch, and the image on the left shows where that ranch is in the continental US. You can see it's kind of in a mountainous region. So to determine whether or not spurge was present at each of the sites that we surveyed, we walked around to each of the 40 sites and manually determined whether or not the plant existed. So as you can imagine, this is very time consuming. If we don't think that a plant exists within a plot, we would have to do a really thorough search to make sure that we might not be missing one species of plant. So it's very impractical to gather a large data set for this type of thing. Another thing that we did when we were surveying the site is we plotted this 4x4 grid of paper plates on the ground that you can see on the left here. And this is also surprisingly time-consuming because in order to do this, we needed to put the paper plates at very precise GPS locations in order for each plot to have equal area. And this means that we walked around with these like big GPS sticks, which they're very like hard to control. So, but another thing is that we would plot these paper plates into the ground, and then there are wild horses in Montana. And the horses would walk up and eat the paper plates. So sometimes we would have to plot the paper plates several times. So this data set took quite a while to gather, as you can imagine. So once we had plotted these paper plates, we would we would image all of the areas we surveyed with a drone. We would take images at both 50 meters above the ground and 100 meters above the ground. But we ultimately used the 50-meter images for testing with Diffusion. And here's the drone we used, and you can see the landscape that leafy spurge is in. Okay, so after getting each 9x9 crop We would further subdivide this region into 4 squares with a size approximately 250 by 250 pixels or 3.5 by 3.5 meters. And in each of these squares, we would also verify whether or not spurge is present or not. So one of the major advantages to this leafy spurge data set is that it's very distinct from any other data that exists, as Brandon mentioned earlier. So in the top left is our image of leafy spurge, and then the rest of these images are images of spurge from existing data sets. And as you can see, nothing really compares to our image, because these other images are mostly close-up images of spurge, whereas ours is an aerial image taken several meters above the ground. So this makes this well-studied or well-suited for few-shot research because it's out of the domain of diffusion models. So if you tell a diffusion model to generate an image of leafy spurge, it's not going to know what to do without the use of our method. So, as Brandon also mentioned earlier, we have very good results on our leafy spurge data set. And also here we can see what Brandon was talking about with the adaptability of Diffusion. So in the top left here, this is a generation that Diffusion made, just like saying an image of and then the token. But the other 3 images, we've added an image of spurge with mountains or with grassland or with snow. And one of the things here is that all the images that we have in the spurge dataset were taken at about 11 in the morning on a sunny day. So the model has no prior concept of like snow in the spurge dataset. But as you can see, Stable Diffusion is still able to generate images with snow or with grassland or images that look like there's a mountain. Ecologists are now working on a second version of this leafy spurge dataset. It's going to be much more detailed. We're going to, instead of mapping out 40 separate plots, we're going to map out one much larger area. We plan to release this dataset in the near future. Another thing about this dataset is that it has 3D terrain. So as you can see here, we have a 3D model of the landscape. We've created this using various angles from different drone images to generate exactly the height of each plot of land. And then we've also turned this into a 2D ortho image. So this is a 2D image, but it has height information as well. So another thing in this new data set that is different from our old data set is that rather than in each subdivision determining whether or not leafy spurge is present, we're going to have fine-scale classification of exactly where leafy spurge is present or not. So as you can see here, the highlighted red areas denote leafy spurge plants. And this is very important for the practical applications of this data set. So what ecologists want to do with this is, as I mentioned, leafy spurge is an invasive plant, and the ranch we worked with is a conservation ranch. So their goal is to eliminate leafy spurge and restore the natural habitat of Montana. So for them, they want to be able to fly a drone, have it detect exactly where leafy spurge is, and then exterminate that plant manually. So this is very important for the ecologists. The conservation ranch that we worked with to collect this data set is called MPG Ranch. MPG Ranch has several other data sets that we think are of value to research and few-shot classification. Especially I want to talk about this bear data set that you can see in the top right here. So ecologists at MPG Ranch are interested in identification of bears from camera images, but they're not just interested in determining whether an image has a bear or not. They want to identify or see if they can identify specific bears so that they can track bear migration patterns and bear behavior. So we're interested in potentially developing a model to recognize specific bears as well. All right, that's all I have. I'll open the floor now to questions. You can find our code on the QR code. Thank you for listening.
Thank you so much for the great talk. Any questions?